Today we are looking at visual generation unlocks human-like reasoning through multimodal world models by Zhelong Wu, Mingsheng Long, and the team at Tsinghua University and ByteDance Seed.
And this paper, it's a pretty fundamental challenge to the way we've been thinking, especially with the dominance of verbal chain of thought.
Yeah.
The core idea is that for tasks that are, grounded in the physical world, models shouldn't just talk through the problem. They need to actually visualize it.
So they're proposing these unified multimodal models that do something called interleaved chain of thought.
Exactly, where the model is generating actual images as intermediate reasoning steps, not just, another block of text.
And the big result, the headline, is really the validation of what they call the visual superiority hypothesis.
It is. They show that this kind of visual world modeling just massively outperforms verbal reasoning on tasks needing spatial dynamics.
Things like folding paper or tracking a bouncing ball.
Yeah, because the visual representation breaks through those information bottlenecks you get with text. But, and this is what makes the paper so good, it doesn't help on everything. For simple grid tasks, like mazes, they found it offered no advantage. And this leads to this really fascinating discovery about implicit world models just hiding in the model's layers.
So if the problem is simple enough, trying to visualize it just adds noise.
Yeah.
But for complex physics, you really have to think in pixels.
That's the 1-minute summary.
All right, let's really tear this apart now. For the last couple of years, it feels like everyone's been obsessed with chain of thought. Just get the model to think step by step in text.
And it works for a lot of things.
For a lot of things.
Yeah.
But this paper argues that for spatial intelligence, text is, well, it's actually a terrible format.
It really is. It's like the difference between describing a complex machine over the phone versus just sending a schematic. The authors are pointing at a huge gap in the current landscape. We know LLMs and even the big vision language models, the VLMs. They're great at abstract stuff.
Like coding, math.
Exactly, because those are symbolic domains. They're sort of native to language. But these same models completely fall apart when it comes to spatial intelligence.
You mean like if I ask a model to predict how spilled water spreads on a table?
Yes, or how a piece of paper looks after 10 folds in a hole punch. The purely verbal models, they just can't do it.
Because even today's VLMs are mostly just mapping an image to a text embedding.
Right.
They turn the visual world into a, quote, linguistic space and then try to reason there.
Precisely. And the authors argue it's not how we do it. They bring up dual coding theory from human cognition.
Okay.
The idea is that humans use two totally distinct channels, a verbal one for symbols and an imagery one for, visual stuff. When you're trying to figure out if a sofa will fit through a door, you aren't writing a paragraph in your head.
No, you're running a mental simulation. You can almost see it, right?
Yeah.
You're rotating it in your mind's eye.
That's the mental sandbox. And the goal here is to get AI to do the same, to move from what they call verbal world models, describing the world in text, to visual world models, where the model generates the state as actual pixels.
And they formalize this. This isn't just hand-waving.
Oh, no. They get deep into the math.
So let's get into that formulation. They define the world as a MOMDP.
A multi-observable Markov decision process. It sounds like a mouthful, but the concept is actually pretty elegant.
Break it down.
The core idea is that the true state of the world is hidden. The ground truth of where every single atom is, we never see that full state. The AI doesn't either.
We only get partial glimpses.
We only perceive it through observations or views. And a view could be an image from your eyes, or it could be a text description you read.
Okay, so a model needs two core capabilities to handle this.
Two atomic capabilities, yes. First is world reconstruction. So, can you infer the complete structure from a partial view? If I show you the front of a stack of Legos, can you imagine what the back looks like?
So encode observations to some internal state, and then decode that into a new view.
You got it. And the second capability is world simulation. That's predicting the future. If I take an action like folding this paper, what's the next state? Formally, it's predicting the next observation, given the history of observations and actions.
So how does this change the definition of a reasoning process? Because we usually just think of it as, a stream of text.
They redefine it. A reasoning chain isn't just text anymore. It's a sequence, R equals a series of pairs, R101, R2, O2, and so on.
Where the R is the logic.
The text part, yeah. And O is the observation.
I see. So in a verbal world model, that observation, that O, is just a text description. It's
Yeah.
something like, the ball is now at coordinate 5, 10.
Correct. But in their visual world model, O is a generated image. The model actually draws the ball at 5, 10, and they even define a third type.
Implicit world modeling.
Right, which is where O is just empty. The model doesn't show its work at all. It just updates its internal state and moves on.
This all leads to their central claim, the visual superiority hypothesis. Why, though? Why is generating pixels better than generating text? I mean, text is so much cheaper to compute.
It really comes down to two things they lay out: informativeness and prior knowledge. They introduce Theorem 1, which is this really neat error decomposition. The total error in a task breaks down into reasoning errors plus world modeling errors.
Okay, what's that trade-off?
So think of reasoning error as ambiguity. Text has a really high reasoning error for spatial stuff because it's lossy.
How so?
If I say the paper is folded in half diagonally, there's still, a couple ways it could look. But if I show you an image of it, there's zero ambiguity. The visual is high fidelity.
But that's where the trade-off comes in, with the world modeling error.
Exactly. When you choose to generate an image, you introduce the risk of generating the wrong image. Maybe your drawing is bad. That's the world modeling error. If the image is wrong, your reasoning based on it will be wrong.
So the whole hypothesis only works if the benefit of the image's clarity outweighs the risk of the model messing up the drawing.
That's the core tension. And their Theorem 2 kind of gives the condition for that. It shows that explicit observations reduce that reasoning uncertainty if the observation has relevant info. And their argument is that text just lit a noose. It suffers from a representational bottleneck.
It's the whole "a picture is worth 1,000 words" argument, but for AI.
Literally.
Yeah.
But there's a deeper point about prior knowledge. The model probably hasn't read enough text describing the physics of a bouncing ball to perfectly simulate it, but it's seen millions of videos of bouncing balls during pre-training.
So the visual generator has kind of physical intuition about things like rotation, reflection, gravity.
An intuition that the text generator just doesn't have. The visual priors are just so much stronger for those geometric transformations.
So to test all this, they couldn't just use like MMLU or something. They had to build their own benchmark.
Yeah, they built VisWorld-Eval. The standard benchmarks are too focused on, simple object recognition. They needed tasks that require actual simulation.
What's in the suite?
So for simulation, they have paper folding, which is just brutal for text models. They have multi-hop manipulation, which is moving objects in a 3D scene. And ball tracking, which is pure physics.
And for the other capability, reconstruction.
They have a task called Cube 3 View. You see a stack of blocks from one angle and have to predict another. And MMSI, which is more real-world spatial reasoning with camera.
And then, of course, the classics.
Yep, the grid tasks, Maze and Sokoban.
And the model they put through this gauntlet.
They used Bagel, which is a really strong open-source unified multimodal model. They trained it with supervised fine-tuning, SFT, on these reasoning paths. The key thing is that the loss function included flow matching loss for the visual parts to make sure the generated images were actually high quality.
All right, let's get to the results. Where did the visual approach just dominate?
On the simulation tasks, it was a blowout. Take paper folding. The visual world modeling. It wasn't just better, it massively outperformed the verbal models.
Why, though? What specifically was the verbal model getting wrong?
It just can't describe complex contours. I mean, imagine trying to describe in words exactly where the creases and holes are on a piece of origami after a few folds. A crease begins at coordinate XY at a 45-degree angle. It's a nightmare.
The linguistic representation is just too sparse.
Right. The visual model doesn't have to describe it. It just unfolds the paper in its imagination. It generates an image of the final flat paper with the holes.
And what about something like ball tracking?
Oh, pure verbal reasoning was a total failure. It just hallucinates. It tries to do like physics calculations and text tokens, and it just can't. The visual model, on the other hand, leverages those physics priors we were talking about. It draws the ball bouncing. It's seen it a million times.
And there was a wild statistic in the paper about sample efficiency for paper folding.
This was really impressive. The visual world model got the same accuracy as the verbal one using 4 times less training data.
Wow. So a single image provides a set of constraints on the problem that would take paragraphs of text to establish.
Exactly. It just learns faster because the visual modality is a more natural fit for that kind of problem.
And on the reconstruction side, the cube task.
Visual one there too, much higher fidelity. But they found this really specific, cool insight they called the mirroring insight.
This is where it gets super interesting.
It is. So about half the samples in that cube task were simple mirroring, just imagining the view from the exact opposite side. The verbal models really struggled. They had to logically deduce, okay, if this block is on the left in the input, it must be on the right in the output.
Which sounds simple for us, but for a model, tracking that kind of spatial logic in text is really hard.
It's very hard. But for the visual model, flipping an image is a completely trivial transformation for a diffusion or flow model. It didn't need logic. It just applied a learned visual transformation. It just flipped the whole generation.
Okay, so visual is the clear winner for anything involving physics, 3D space, complex geometry. But it didn't win everywhere.
No, it didn't. And honestly, this is the most important part of the paper, scientifically. On the grid world tasks, maze and Sokoban, the visual approach offered zero advantage. Sometimes it was actually worse.
Worse than the text-based one.
Worse than text, and specifically worse than the implicit world model.
The implicit one. That's where the model doesn't output any state description at all, right? It just thinks internally and gives you the next move.
That's the one. The authors call it the grid world anomaly. And it's a great question. Why would visualizing a maze not help you solve it? I mean, I solve mazes visually.
So to figure this out, they basically did brain surgery on the model.
They did. They ran what's called a probe experiment. This is a really deep technical insight. The hypothesis was maybe the model is already tracking the agent's XY coordinates internally in its hidden states.
So they trained these little simple MLPs, the probes, to just look at the hidden layers of the standard bagel model while it was solving a maze.
Yep. And what they found was that the pre-trained model already had these emergent representations of the maze state. It already knew where it was.
It had a map in it too.
An emergent map, exactly. Yeah. And then when they fine-tuned it, that internal map became almost perfect.
So if the model already has a perfect idea of its coordinates in its hidden state, then forcing it to generate a whole image of the maze is just redundant.
It's worse than redundant. It's noise. Remember Theorem 1 and the error decomposition?
Right.
If you force the model to generate an image, you introduce the risk that it generates the wrong image. The world modeling error.
You might draw the wall in the wrong place by mistake.
Exactly. And since the state of a maze is just a simple, low-dimensional coordinate X, Y text or an implicit state can represent that perfectly, generating a whole image is complete overkill. It introduces unnecessary error without adding any new useful information.
That is such a critical nuance. Visual isn't always better. It's better when the state is complex and high-dimensional, like a crumpled piece of paper. But for a simple grid, you're better off keeping it implicit.
It's a perfect validation of their trade-off theory. The smartest model is the one that knows when to just calculate and when to stop calculating and start imagining.
And they didn't just stop with supervised fine-tuning. They also applied reinforcement learning to this.
RLVR, yeah. Reinforcement learning from verifiable rewards. They used the GRPO algorithm.
But there was a catch with how they applied the RL, wasn't there?
A pretty big one, a limitation. They only optimized the verbal tokens with RL, the visual generation. They couldn't really reward it directly. I mean, how do you write a reward function that knows if a generated image of a half-unfolded paper is mathematically correct?
Right. You can't just do a pixel-by-pixel comparison with some ground truth image.
Exactly. So they just regularized the visual generation to keep it from drifting too far off, but they didn't directly reward it for being right.
And what was the result of that?
RLVR improved performance for everyone across the board, but the gap between the methods stayed the same. The visual world models still beat the verbal ones on the hard physical tasks, even though only the text was getting that direct RL boost.
Which implies that the visual generation is acting like a scaffold for the reasoning. Even if it's not being directly optimized, just having that image there helps the text-based logic stay on track.
That's the implication. They also ran a comparison against a pure VLM, Quinn 2.5 VL7B.
A real heavyweight.
A heavyweight. And their post-trained bagel, the one with visual generation, still outperformed the pure VLM on these hard tasks. It proves that this generating-to-think idea is a viable strategy. It's not just about scale, it's about changing how the model computes at inference time.
We're spending compute cycles to generate images, to think better.
To get a better final answer, yes.
So if we zoom out, what are the big implications here for the future of AI?
I mean, for embodied AI and robotics, this is massive.
Right. If you want a robot to be able to clear a dinner table, it needs to understand what happens if it knocks over the glass of milk.
It has to. It needs to imagine that outcome before it acts. This paper is basically a roadmap for giving AI that kind of human-like physical intelligence. It's about moving beyond what they call the linguistic constraints of current LLMs. You can't just describe physics into existence with text.
It really pushes back on that whole text is all you need mentality.
It absolutely does. The paper points towards a kind of division of labor. For math, for logic, sure, use symbols, use text, but for physics, for space, for geometry, you have to use images.
It's almost like a computational version of the right brain, left brain distinction.
You could think of it that way, yeah. If AGI is the goal, we might need to stop treating every problem as a language problem. We need to start treating imagination, and I mean literal pixel generation, as a core reasoning primitive.
That is a wild thought. That the path to more intelligent AI involves a kind of controlled, purposeful hallucination of images to solve problems.
Well, what is human imagination? It's us hallucinating possible futures so we can pick the best one and avoid the bad ones. AI is just finally learning to do the same thing.
We'll leave you with that thought to chew on. The paper is Visual Generation Unlocks Human-Like Reasoning. And if you really want to geek out, I highly recommend checking out Theorem 1 and the math behind the error bounds.
It's a fantastic piece of work, a must-read.
Thanks for listening to AI Paper Podcasts. We'll catch you on the next deep dive.